All right, recording is rolling. It is Monday, December 18th. We're gonna do some midterm review today. Remind you guys that the schedule looks like this week. It's a different type of schedule. I did post this to Google Classroom, I think a couple weeks back, I find. Right. So tomorrow, when you show up 8:45, which class are you going to tomorrow morning? Second period. Then each class period's about 33 minutes. Ooh, you're having lunch with sixth period. Hey, lunch with sixth period. I tell you, I guess I have C lunch. I have third lunch. So for my sixth period tomorrow, come to this class period, hang out about an hour, and then they go to lunch. Right? All right, and then your first period exam is at the end of the day. That's 2 hours. Each day after that, Wednesday, Thursday, Friday is going to be a short day. We're getting out at 2:15, Wednesday, Thursday, and Friday. So a couple classes each one of these. All right, so you guys got that thing. All right, then this exam. All right, so I'm going to try to do at least 1 or 2 examples from each of these sections. We got measurement, SI system, units, vector components. Right? Then we did kinematic motion, that's linear motion, projectiles, right? There was maybe acceleration, possibly, right? Distance equals speed times time. It's not. We got dynamics, Newton's laws of motion, forces, free body diagrams. Remember Atwoods, remember inclines. Right? There is centripetal force, circular motion we got into. Combine that with universal gravitation, made orbits. Can you guys drive orbital speed from scratch? I'll have you guys do that later today. Energy and work. You guys remember energy is conserved. Again, set of conservation of energy equations. Work is a transfer of energy. Ooh, force versus distance graph, right? The area under that curve. Right? Then collisions, momentum, impulse, right? Momentum is conserved. It's a vector quantity, right? Keep track of what's going forward or backward for a collision. Impulse is a transfer of momentum. If you have like an open system, that could be the area under force versus time graph. Okay? And then rotational dynamics we did most recently that involved torque, angular momentum, that sort of stuff. Right? We also did some rotational kinematics along the way. All right, so with that, all right, let's do this again. Try to keep a fast pace today. I usually tell you guys, see if you can stay a step or two ahead of me. So if you can, here we go. All right, let's start with, and I'm going to give you guys a pretty good review that maybe won't exactly give everything away tomorrow, but when you see your midterm tomorrow, like, okay, this is pretty good review here. But if you have a plane that's going 40 meter per second straight north, and then it runs into a crosswind going 30 meter per second straight east. Yeah, you knew the question. What's the ground speed of the plane? Right. So you say how fast is shadow going across the ground if you point a radar gun at it from the ground. Yeah, you're right. This is Pythagorean theorem. So here's Pythagorean theorem. All right, we're getting 50 meter per second is the ground speed of the plane. Right. Oh, so here's velocity of plane relative to air plus velocity of air relative to ground gives you velocity of plane relative to ground. Notice I'm saying velocity. That's not just speed. That's also what? Direction. How do you get this angle theta? Yeah, you could do like an inverse tan of opposite over adjacent. Did you guys remember what that angle is for a 3, 4, 5 proportion triangle? About 37 degrees. I'll say like east of north. There you go. Right. The other angle is about 53 degrees. All right. So there's a good starter, right? There's a good warm up. Right. You guys want to do, say a little bit more complicated version of that. Let's do a lantern hangs from 2 ropes. You guys want to do a lantern hangs from 2 ropes? Okay. I'm already thinking ahead a little bit. I'm going to introduce a Cartesian system, which maybe this is a textbook question. I would do this after you get the picture, but you guys know we're going to use this to analyze forces, force components. Right? Maybe there's some knot where I have like 3 ropes come together. Right? 1 rope straight down. Right? I'll say here, maybe there's like a lantern here. It's hanging. It's all shiny. It's like let's give it a weight of 100 newtons. Right? Nice round 100 newtons. Boom. There you go. Right? So I guess like 10 of these. Ooh, I guess it's a really heavy lantern. Right? Things like that. And then let's say I got a couple of ropes. Now this one here, I'll simplify this a bit. Right, I'm going to put some symmetry to this one. Right? And tell you guys, well, you're not always going to get symmetry, but I guess on this review you are. Right? So I'm going to make both of these supporting ropes 30 degrees from the vertical. I see 30 degrees from the vertical. Right? Hey, did you guys see just based on symmetry that this tension on the left, this tension on the right are the same tension? right? Okay. So I'll call it Ft, just tension force, right? Now, if these two angles were different than each other, could I go tension left and tension right? And those would be two separate values we'd have to solve for? Have to be right, right? And my question is going to be, what is the tension? That's the question. What's the tension, right? And your framework for solving this is, well, equilibrium. So the sum of forces goes to 0 newtons. And that's true, well, here I have a 2D system set up with Cartesian axes. So let's go in each direction. Sum of forces in the x goes to 0. Sum of forces in the y direction goes to 0 newtons, right? Again, if these angles were different from each other, I'd have to use both of these in a system of equations. But for this review, a little simplified, right? Really, you can solve this with just one of these. I'll show you guys how, right? Again, hopefully you guys are staying a step ahead of me. You know, I'm keeping a pretty good clip right here, right? Can I break these tensions into components that align with the Cartesian system? Like this guy's pulling a little bit left and a little bit up. And this guy's pulling a little bit right, a little bit up. Right? You guys see that? Right. So now I'm thinking, how much left up? How much right up? You guys see that? Right. Hey guys, what is this angle right here? 30 degrees. I guess this one would also be 30 degrees, wouldn't it? Right. What is this angle right here? 60 degrees, because it's complementary. Because I've got some right triangle on, right? Could this here, well, I see the left and right obviously cancel out. I mean, probably get that from symmetry. That's what this first condition right here says, right? Some of the forces in the x goes 0, right? But you know what? I do have this vertical information right here, this weight. So can I figure out, I guess, one or both of these components, vertical, and then play off this condition here and solve for the tension? Okay. So this component, in terms of the tension, I call this tension force, which we're solving for, multiplied by what? Cosine of 30 degrees. All right, winner. Cosine 30 degrees. Right. Or you could have said sine of 60 degrees. That would work too. And I guess same story for this guy right here. This is tension force times cosine of 30 degrees also, isn't it? Okay. All right. So let's map this thing. If I play off the second condition right here, the fact that the sum of the forces in the vertical direction goes to 0, I'm going to pull that out. Say, well, that means that these two upper components has to balance with the downward full weight. Right? Right. So Ft cosine 30 degrees, right? And then plus another one. So maybe I can just say times 2, because there's 2 of those. Right? Minus 100 Newton weight goes to 0 newtons. Right? We're gonna be set. That's one way to set it up. Think of it, right? This up and this up balances with this down. Right? So add 100 over. Let's see what it. Let me push all this together. Normally I solve in terms of components, but let's get some numbers along the way. So this all comes out to 1.73, and then times the tension force. And I'll slide that 100 newtons over and say that's equal to 100 newtons. Is that all right? Okay. Divide by sides, coefficient 100 divided by that. Okay. I'm getting the tension force in each rope is 57.7 newtons. That was an answer choice. Multiple choice, I might be, say, 58 newtons. That should work too, right? 58 newtons. Okay. Right. Whenever you get an answer in physics, stand back and say, does that look about right? Right. Well, how about this? I can frame it like this. If these two ropes were exactly vertical, I know it would be 50 newtons and 50 newtons, right? Sort of reminds me of a pulley system, the 2-to-1 pulley system, right? 50-50 to balance out this 100. The fact that they're spread at some angle, I bet it's going to be a little bit more than 50 newtons each. Oh, yeah, and it sure is about 58 newtons. Right, you guys get there? You guys can solve that one? Okay. All right, you guys ready for a kinematic? Let's drop some balls off some cliffs. Ball off a cliff. Okay. Cliff. Ball. I'm going to drop this ball off this cliff. Let's give the cliff a height of, 100 meters. And I want to know what is the speed of the ball, call it the final, right? The speed of the ball after it's fallen off a 100-meter tall cliff. Okay? I can think of 2 ways to solve this. If I'm going in order by the units, maybe a kinematic approach to it, right? Could be one way to solve it. We'll come back to another way later. Right? Now, kinematic. Remember those 3 kinematic equations, juggling 5 variables? It might help maybe to make a little tax VB checklist. Right, so what I'm doing right now, you don't necessarily have to do this. So you could skip past a step if it's all right with you. Right? But sometimes it's helpful to get a nice checklist. Okay, here's what I have. Here's what I'm solving for. Right? So now the only number I've explicitly written here is this one, right? The displacement. So I can call this 100-meter displacement. Okay. And okay, the question is, what is the crash speed? Okay, that's this guy right here. Right? I said we're dropping a ball off a cliff. Now, what could possibly be implied, or you could also know from what I just said? Yeah. Oh, okay. What should I put right here? Okay, 9.8 is a good number. Yeah, I'm gonna go ahead here. I'll tell you guys too. When I plugged all the numbers into Excel, blah 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 blah, I did use 10 meters per second squared for Earth gravity. I did also print that on the midterm tomorrow, but you guys know tomorrow. Right? If you use 9.8, you'll probably get some of this plenty close enough. But if you use 10, you should get exactly what I got for the multiple choice answers tomorrow. Okay? Right. So you drop a ball off a cliff. You know one more thing, which is, is 0 meters per second. That comes from the word dropped, right? We see dropped, like, right? Or starts from rest, right? Okay. Okay. So we got these three, so 3 kinematic variables we've identified. That means this is solvable, right? Notice, I mean, it's going to take some time for the ball to fall, but notice I've neither been given or asked for a time, which is probably a hint that we're going to use that third kinematic expression. Okay. And normally slow mo this thing a bit, but I'm going to cut straight to it. Right. Hopefully you guys have those 3 kinematic formulas memorized, but if not, you guys know it's open notes anyway. And so open notes exam, as long as you know like where to find it. Probably most important for, especially if you're AP is, you guys know on the actual AP exam, open a little bit notes, is open this page, they'll give you this. So can you identify where to find these, right? AP type C is a little bit different than I showed you in class. Right? They do it in terms of position, set displacement. They rearrange them a little bit different order, right? But know where those are and how to apply them. So one way or another, you come up with this expression. That guy goes away. Right? Solve for the crash speed. Crash speed is square root 2ax. Plug in some numbers. Let's go 10 meter per second squared for Earth gravity. Same thing on the midterm tomorrow. And a vertical displacement 100 meters. Put it all together. See what we're going to get. 2000. Okay. Looking at 44.7 meters per second. Of course, we're ignoring air drag. Right, so ignoring air drag. Okay. So maybe 44, 45 meters per second, somewhere there. We can solve multiple choice for either 44 or 45 meters per second. Okay, that's probably it. Oh, but I said there was another way you could also solve the same question. What's the other approach you could do? Conservation of energy. What kind of energy at the top? MGH. What kind of energy at the bottom? 1/2 mv squared. Let's do it that way. Sum of energy initial equals sum of energy. Well, I'm saying sum of as it's different things we're adding together, but really it's only one type here and one type here. You guys told me exactly. It said it's all MGH at the top. It's all 1/2 mv squared at the bottom. Oh, I never gave you the mass of the ball. Doesn't matter. Final velocity times 2 square root. V is C. So it's going to be a square root. You're going to have a 2, going to G. Hey, square root 2GH. Hey, didn't I make a leaning tower poster where that was the answer for the leaning tower? See a leaning tower somewhere? Right? Hey, oh, square root 2GH. That's the same thing as what we got over here. Square root 2AX. Same thing. Right? Gravity field is a type of acceleration. Height of the cliff is a type of vertical displacement. Boom, boom. Right? So you guys good with the off cliff? Right? What if I had a question? How fast? Let's say you're at the bottom of the cliff, right? And you got a friend at the top saying, "Hey, throw me that ball." How fast do you have to throw the ball so that it gets to him, so you can reach out and grab the ball? It's the same answer. Same answer. Same answer. Or you could use that method. Same answer. Okay. All right. Let's go 2D. I remember we did a lab where we went up to the balcony. I had you guys blast some balls off the balcony. You guys remember those launchers? Okay. The question, the target question, the same question here is, what's the blast speed? Let's say we aim this thing straight horizontal. Now, pow. Oh, and somewhere there. Okay. So V blast. Okay. Let's say that's the question, trying to figure out the blast speed, right? Or aim it straight horizontal. Okay. So I have to give you some things. Let's say I tell you the height of this cliff is like 45 meters. And also I'll tell you that this horizontal displacement where it lands is 60 meters. Right? Let's say that's as much as I explicitly give you. right? You want to figure out the blast speed, right? So hopefully you're already chugging through your mind how to solve this. Yeah, revealed is kind of fast clip here. Here's what I'm thinking. Whatever the blast speed is also the horizontal component velocity because we're aiming the straight horizontal, right? So it's going to be the same horizontal velocity all the way across, right? Which is this horizontal displacement, which you guys measured either with a meter stick or a trundle wheel, right? You guys remember that spotted the ball? So, okay, how far to go? Divided by the time of fall. Now, I recommended you guys not use a stopwatch for this because that'd be pretty inaccurate for this time. But you can calculate the time of fall based on this drop height. Guys remember that? You took a meter stick also and walked up the stairs and And now I think that balcony out there was about 4 meters tall. Here I'm showing something about like 10 times that. Right, so let's put it all together. This is going to be 2 parts. I'm going to use vertical information to determine the time of fall. And then I'll switch over to horizontal and say, something about how fast it's going across. So vertical, can I say height of fall is 1/2 gt squared? That's a simplified version of one of those kinematic expressions. You guys remember the one that said x equals v naught t plus half at squared, right? Why am I calling initial velocity 0 and just getting rid of that term? Because if I blast it horizontal, what's the initial component of velocity in the vertical direction? 0. It doesn't matter how fast this guy's blasting horizontal. Vertically speaking, it's 0 meters per second. Right, okay. Guys, if you blast something horizontal and you drop a ball at the same time, who hits the ground first? It's a tie, which means they have the exact same vertical motion. So whether you drop a ball or blast it horizontal, you can still use this for vertical, right? It doesn't matter how fast it's blasted horizontal. It's not orbiting the Earth. It's not going to like suborbital. Okay. So we're solving for time here. Let's do 45 meters. It falls. It's picking up at a rate 10 meter per second squared. Time squared. Guys, what's 2 times 45? Divide by 10. Square root. 3 seconds. Hey, takes 3 seconds to fall 45 meters. Maybe you remember dropping a ball off a cliff. I made a whole table, right? Made some graphs, right? If it was a super tall cliff, you drop, it falls 3 seconds, falls 45 meters. Right? That's a college equation too, isn't it? That college. We're going to switch over horizontal. Horizontal. Right? I could say some version of distance equals speed times time. Or I could do that, right? D equals v sub x times t, right? Or rearrange that and get v sub x, which is the blast speed. It's the same thing. V sub x, right? Is horizontal displacement divided by the fall time. Right? Notice I haven't said anything about acceleration, which I don't need to. This is after it's left the cannon barrel, of course. There is no horizontal acceleration. We're ignoring air drag. Gravity only pulls vertically, right? So this is the only equation that applies horizontally to projectiles. Right? So let's do falls 45 meters. No, sorry. So just cross check. 60 meters. Went across 60 meters and did that all in 3 seconds. Is that like 20 meters per second? Is the blast speed? Right? Blast speed 20 meters per second. Right, you guys do that? Like that far and that much time. All right. Let's do an Atwood. Let's do a classic Atwood here. Classic Atwood. So let's say like a massless frictionless pulley. I got like a negligible mass string. Right. Somebody's holding up the pulley, so the pulley system's fixed in place. Okay. So on a couple of blocks here. So big block, little block. There you go. Okay. Let's go some masses. Let's call this guy a mass of 4 kilogram. Call this guy a mass of like 1 kilogram. Right? There's quite a few questions I could ask about this. Right? But the classic questions are, let's answer the classic questions. Okay. What is, say, like the downward acceleration of the large block is probably how it would be phrased. But I'll just say, what is the acceleration? Right? Like say downward acceleration of the large block. Okay. And then the follow-up question could be, what is the tension in the ropes connecting, the tension in the string connecting? I'll say force, tension, force. Okay. Okay. Let's do free body diagram for this. Free body diagram. Okay. Now, if I'm just focused on the external forces, which I can use to figure out the acceleration from the system's point of view. Okay. How many newtons weight is this right here? 40 newtons, right? mg. Okay. How many newtons weight is this right here? 10 newtons. Okay. If I drew that exactly to scale, This one should be 4 times the magnitude of that one. Okay. Oh, so I'm going to start focusing on those. Right now, later on, when we get to this other question, what is the tension force? Okay, maybe I have something like that too, right? Okay. So if it's an ideal type situation, then I can say that there's only one tension in this rope, one tension in this string. I'll label it FT. FT. It's the same tension, right? As long as this pulley wheel has like no friction, no rotational inertia. Okay, so okay. So, and notice the tension force is going to be like the Goldilocks force, right? So it's larger than the small weight, but smaller than the large weight, so this thing can accelerate it. Okay. So there we go. Now there's 2 main approaches you can do for this, right? One is that you can create a system of equations, do a free body diagram here, and do a system of equations. Right? And you get kind of both of the answers simultaneously, sort of. Right? I'm going to do this the way I normally do it with you guys, which is I'll start from a large picture, like a macro system's point of view, which is we'll say Newton's second law of motion as it applies to the whole system. So these 2 weights are acting as external forces. I'm going to start by ignoring the tension because I'll say that this holds everything together. Right? So these 2 guys are like a tug of war, 40 newtons clockwise versus 10 newtons counterclockwise. Okay, so I'm going to go net force over total mass. Now net force vector quantity is going to subtract 40 minus 10 clockwise versus counterclockwise. 40 newtons minus 10 newtons. Right. The total mass it acts on, the total inertia it's moving around, well, that's a scalar, so I'm just going to add it up. 4 kg plus 1 kg. Right. And when you guys did this lab, I had you guys first figure out this out empirically what was the acceleration. So, well, see, tag on some weights, whatever, it's going to fall, it's going to change some distance and some time interval with the stopwatch, and you can calculate the acceleration, and then go back and say, okay, well, I put on these masses and see if you guys could come up with basically this, right? So difference in weights over sum of masses will get you the classic Atwood, right? So we got here, we've got 30 newtons acting on 5 kilograms. Is that 30 newtons, 5 kilograms? Okay, so what's the acceleration? 6 meters per second squared. Newton per kilogram, is that the same thing as meters per second squared? Same thing. Okay. Does that look like it makes about sense? Well, if these 2 are same mass, same weight, this would be 0 meters per second squared. Right? And then if you put all the weight on one side, this would be 10 meters per second squared. Yeah, okay, so it's, okay, yeah, that looks about right. Right. So we'll go with that. That looks reasonable. Right? Follow-up question, what's the tension in the string? Now, tension, so what I would do at this point though was shift my perspective to just one of the blocks. So eeny, meeny, miny, mo. How about this guy right here? Now this block right here, I can still do Newton's second law of motion. The net force equals mass times acceleration, but now it's only going to apply to that single block. Net force, I see the tension force up minus the weight down equals, okay, then put in 1 kilogram for the mass, and then for the acceleration, well, I know it's going to accelerate this many meters per second squared right there. Okay. That 6 newtons right there, kilogram meter per second squared, that's Newton. 6 plus 10, tension force is 16 newtons. Right? Does that work from the other point of view of the other block? What if I pick the other block? Would I still get 16 newtons? I mean, I should. So it's the same tension force that string. Yeah, I'll check my answer this way. Let me find net force over total mass of this block, and I better get 6 meters per second squared. Right? So that'd be 40 minus 16. 40 minus 16. What is that, like 24 newtons net force? Right? Acting on 4 kilograms, so divide by 4. So Newton's second law of motion. Right? Right? I've got to get 6 meters per second squared. That would confirm that I did everything right. Yeah, 6 meters per second squared, because it matches. Right? Okay. Guys good? Okay. Could I ask you guys some follow-up questions about the Atwood? Could I ask you guys, like how far has it fallen after some time, or how fast after some time, or how fast after some distance moved? And you could just maybe start with this and run back to kinematic, right? Do something like that, right? Or that last question I asked, how fast is it moving after some distance move? You could alternatively use conservation of energy to approach that, right? We did something like that recently too. Okay. All right, so like that. All right, let's go. Let's do some inclines. Inclines. Got a couple of incline questions for you guys. Okay. Let's start with kind of one of the first labs, one of the big labs that you guys did in this class was rolling cars down inclines. Okay. Just a little tiny wheel, so the rotational inertia is negligible, right? But this car has some mass, right? And let's say this is at some angle. So let's say theta equals 30 degrees is a nice round angle, right? So that's a really nice angle, shows up quite a bit. Right? Let's give this car a mass of 5 kilograms just to have a number. Although you guys probably remember that that's going to end up canceling out at the end. Okay? So my question could be, what is the acceleration of the car? The acceleration. Okay. Now, if you see an incline, I told you guys introduce a Cartesian system that aligns parallel perpendicular to the surface. Okay. So not to gravity in the floor, but to the surface, okay, of that incline. So there's parallel to the incline surface, right? And then perpendicular Cartesian system, right? So that when I draw a bunch of free body diagram vectors, do F, B, D, free body diagram, right? Those vectors are either going to be aligned to that system, or I'm going to break them into components so that they are. Okay, guys, what's one force on this car? It's weight. Yeah. So I'll call that mg, and that's how many newtons for this car? 50 newtons about. Right? What's another force on this car? Friction. Let's say friction is negligible. So I got little wheels on it. Yeah, normal force. Got to have a normal force. Is the normal force a little bit bigger or a little bit smaller than the weight? A little bit smaller in this case. Right? Now, if the car's like making a turn on a banked road, it gets a little bigger. But for just rolling down, I can draw a little bit smaller. If I can tell you exactly what magnitude to draw, if I got that right. If you break the weight into components, that weight is partly pushing the car into the incline, partly pulling it along. Right? Can you guys do that? Notice how I'm pulling my ruler parallel to the surface. Do you guys see parallel? You guys, a lot of students struggle with parallel lines. When you guys take the AP exam, this is, I think it might be the only AP exam where they allow you to use a ruler, right? And I do recommend you guys use a ruler, like a straight edge ruler or straight edge, right? And if you don't have one for whatever reason, you can fold up a piece of paper and use that as a straight edge, right? Right? You guys see parallel. You guys see parallel. I bet the AP grader will be impressed if this is your FRQ and you can draw parallel lines. Like, oh, phew, finally, like, after grade 10 of these, one student can finally draw parallel lines. So many students struggle with parallel lines. Can you guys draw parallel lines? Okay. Guys, what is this angle right here? 30 degrees. It's always a match. Right? That angle is that angle. Okay. So this component right here, is that mg sine theta? Oh, I was going to ask you guys. Oops, I gave it away. Sine theta. But you guys have done it so many times, you could have said that, right? Okay. So 50 newtons times sine of 30 degrees. Hey, I bet you guys can do this without a calculator. What is sine of 30 degrees? Half. Yeah. So this is 25 newtons, right? So let's hold on to that. I bet that's going to be important. Right? So this component right here is pulling with 25 newtons. Okay? And then this component is this mg times cosine of that angle, right? So right now, whatever that happens to be is going to be the normal force, which is less than the weight, because cosine of something is less. Right? Let's figure out what that is. Let's do some numbers. This is going to show up later. So 50 Newton weight times cosine of 30 degrees. I'm looking at 43.3 newtons. So this is 43.3 newtons. Therefore, the normal force must also be 43.3 newtons, so that there's zero net force into and out of the surface, so it's not accelerating that way. Right? Guys see that? Right. Good so far? Good so far? Right. All right. When you guys did this lab originally, it said this was like one of your first labs, you guys were looking at a bunch of kinematic stuff. So how far does it go as a function of time, and how fast was it going? Some of you guys were swapping out the weight of the car, and you guys saw that ended up canceling out at the end. Okay? I don't think we exactly answered the question, what's the acceleration of the car this here, but we got kind of close. Right? But then we got to this dynamic section. Okay? We could do all this analysis, and we can answer this from a Newton's second law perspective. Okay? Newton's second law, acceleration is net force acting on the mass. Right? So what have we got here? Guys, what's the net force acting on that car? How many newtons? 25 newtons. And what's the mass it's acting on? 5 kilograms, right? Is that 5 meters per second squared? Maybe I should say 5.0 if I have like 2 digits to work with. Right? Usually AP exam answers, they have like 2 digits, so probably say 5.0, right? But hang on a minute. remember sine of 30 degrees was half. That looks like half the free fall gravity. Hey, can we kind of back up and solve this in terms of variables? Like the net force, if you kind of go back and substitute, net force is always mg sine theta for this particular setup. And well, the mass is just the mass. Oh, look at that. It's just g sine theta. 10 meters per second squared times half, boom. Okay, you guys see that? Okay, let's do this now. Let's do another incline. I got a different question. Let's get rid of the wheels. Okay, let's go. Oh, you know, maybe I'll do this way. Hope I don't confuse myself. I'm just going to trace over the backside of this paper about that. Okay, let's get rid of those wheels though. Right, let's just have something sliding down. Sliding down. All right. Oh yeah. Oh yeah. Okay. And let's have it slide down at constant velocity. So I'll call it v constant. Right. Now, the fact that it's sliding down at constant velocity, guys, what do you know about the net force? Yeah, 0. Right. Does it matter how fast it's sliding down? No, as long as it's constant velocity, you know the net force is 0. Right. So let's make a new free body diagram. FBD, free body diagram. Okay, so it has some weight here. I made it the same mass as before, 5 kilograms. So I guess it has the same weight, right? So mg would still be 50 newtons. So that's the same. Okay. Let's introduce a Cartesian system, just like before. That runs parallel, perpendicular to the surface. Here's parallel to the surface. Here's perpendicular to surface. Oh, let me fix my camera. Oh wait, is my camera all right? I bumped it. Sorry. Okay. Right, so I know there's maybe I should just go ahead and split this weight into components. Okay? So I can get a real clear idea of what is my normal force, and I think it's going to be a friction force on this one that matters, right? Okay. So here, oh, I meant to give you guys the angle. It's the same angle. Let's go 30 degrees. 30 degrees. Okay. So could this be mg sine theta, which 50 newtons sine 30 degrees, it comes out to 25 newtons, just like before. Okay. And then let's just call this 43.3 newtons because we did that before too, right? I'm using the same type numbers as with the car, right? Only this time I'm saying it's not a car, it's just like a sliding block. Okay. So I can say then normal force is 43.3 newtons, wherever that comes from, mg cosine theta, if you like. And there better be a friction force because you guys told me it's force equilibrium. All the forces balance out. Friction force, which, guys, how many newtons is this friction force? 25 newtons. Yeah, 25 newtons, right? Because it has to be a match, right? So there's 3 forces on this block: the weight, the normal force, and the friction force, right? And they all zero out. Okay. Right. So question: what is the coefficient of kinetic friction between that block and that surface? Right? Now, this is a material question. Like, if you know what materials they are, like, oh, that's a steel block sliding on an aluminum surface, right? At that point, this becomes determinable because those are like known materials, right? With some known value, right? But we're solving this from this. Maybe we don't know what the materials are, right? We're trying this out, right? This was a version of the lab that you guys did. So what is coefficient of kinetic friction? That's the ratio of which 2 forces? Yeah, friction force over normal force. Right? So okay, so that's universally true. Right? I say equals if it's sliding, it's kinetic friction. Right? And here, friction force. Well, if we do the numbers, is that 25 newtons compared to 43.3 newtons? Right? If you're seeing bigger picture in terms of variables, you say, okay, well, that was mg sine theta, that's mg cosine theta. Ooh, I bet one way or another, the mass and gravity field could kind of cancel out. Probably has something to do with just the angle, if you like. Right? I gave you guys more of a numerical type example here. So just continue with that. We'll get 0.577, probably about 0.58, maybe about 0.58. Right. That looks like a pretty reasonable value for a coefficient of friction, kind of in line with a bunch of examples you guys seen throughout the semester. All right, you guys ready to do some gravitation? Gravitation? All right, let's do gravitation. All right, let's say there's this planet, little planet here. Okay. It's got some mass, capital M. It's got some radial size R. And let's throw a little guy up here with mass little m. Right, he's walking around on that planet. Right? Okay, so we're about to get to gravitation type questions. Right. If I want you to use calculation, I will give you this number. Universal gravity constant is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Right. If I expect you to do that calculation, I'll give that to you. Okay. Right. If I ask you guys, what is this guy's weight on this planet? You guys would come up with what expression to answer that question? How about GMM over R squared? That's his weight, right? His weight. What if I asked you guys a little bit different question? What gravity field does he feel walking around? Like if you plug in all the number, what gravity field? GM over R squared, right? Just divide by his own mass, right? Okay, and then you have lots of different masses of the surface. They all experience the same gravity field, right? That's gravity field. Gravity field, something like that, right? Okay, if you plugged in all the numbers for Earth, okay, so universal gravity constant, mass of Earth, radius of Earth, right? You would get what number? Yeah, about 9.8 meter per second squared, okay, something like that. Okay. Let's do a proportional question. You guys know AP really likes proportional questions, right? What if this is some planet X, and the mass of this planet X is 3 times Earth mass? And the radial size of this planet X, well, it's large. Let's make a bigger size volume-wise. Right? 2 times Earth radius, right? Now, I think that makes this like a giant puff planet. I think it has small density, but if you puff up the planet, okay. So yeah, it's heavier, it's bigger size, right? 3 times mass, 2 times Earth's radius, right? Maybe it's like made out of styrofoam or something crazy. Oh, yeah, thank you. What I want to know is, what is the gravity field on this planet X? What's the gravity field right, compared to Earth, right? So here, I'll walk you guys through it. Again, I'm trying to keep a fast clip. You can stay a step ahead of me. Awesome. Right. So the question is, what's the gravity field? I'm going to use this as a model. Right. I'm going to substitute in the planet X values in terms of Earth values. So universal gravity constant, so universal gravity constant. All right, so M. Well, I know mass of planet X in terms of mass of Earth. That's 3 times Earth mass. And then I got 2 times Earth's radius. And okay, and that's being squared. Right? So I can take some numbers out in front. Take this 3 out in front. 2 squared out in front. Is that like a 4? And I got gravity or constant, mass of Earth, radius of Earth squared. Right. Hey, okay, are you guys got that? Right. And then all the stuff I put in parentheses, well, that's just Earth gravity right there, isn't that? So could I say the gravity field on planet X is 3/4 of Earth gravity? Right. Oh, and if you want a numerical value, Earth gravity, about 10 meters per second squared. This could be pretty close to 7.5. I can say meter per second squared. I could also call that what for what? What's the other unit? Newton per kilogram, right? Could be equivalent, something like that. All right. All right. So yeah, so you guys can navigate gravity fields. You guys can do proportional questions, right? Let's figure out something else for this this planet X. Something else, right? Let's figure out orbital speed. Okay. So let's start a new piece of paper here. Here, right-handed, so let me put my picture on the left side so I'm not like covering up what I'm doing. Okay. Let's say there's a satellite that's going just above the surface, kind of like low Earth orbit, I guess, low planet X orbit, right? So that, right, here's the mass of the planet, mass of the satellite, right? So that the radius of orbit, oh yeah, yeah, check out. All right, yeah. Right. So the radius of orbit is pretty close to the radius of the planet, right? Okay. Now remember, we're going mass of planet X is 3 times the mass of Earth, and the radial size of planet X is 2 times the radial size of Earth, right? So, like I remember orbital speed. If you plug in orbital speed, all the values for it. Do you guys remember what orbital speed is, like low Earth orbit? It's about 7,900 meter per second, so something like that, about 8,000 meter per second. Right? So we're going to talk about orbital speed. Orbital speed. Right? Now, this one, AP, you should be able to derive from scratch. Okay. Okay, I wouldn't want to give you guys a head start, but let's just go ahead. Can you guys say centripetal force is provided by gravitational force? You guys could say that. Okay. Centripetal force, what's a good expression for that? mv squared over r. Okay. Also m omega squared times r, but if we're solving for orbital speed, it's probably a v situation, right? And then universal gravity force, could that be g m over r squared, something like that? Mass of the satellite cancels one of the r's. And then orbital speed for a circular orbit is this right here. Okay. Guys, that's a real short proof. Look at there. Boom, boom, boom. Right. That would be a completely fair FRQ. Yeah, so you should be able to do that. But I want to go another step with this. I want to say, well, what is the orbital speed for this planet X compared to Earth? So see, orbital speed for planet X is, right, so that's the square root, universal gravity constant, right? Oh, the mass of this planet is 3 times Earth mass. And the radial size of this planet is 2 times Earth's radius. Put it all together, V or planet X is, so you take the 3 and the 2 out, although still underneath the square root, let's pull out as a number. So you could put that in your calculator, get some number, right? Times, and then all this would be GM on R square root of that, right? V or for Earth. Right, you guys can see it? Right, still substitution at the end. Right? Because everything, this 3 and the 2, otherwise, everything else is just the orbital speed for Earth. Right, like I said, math radius for Earth. Right? Right. So interestingly, interestingly, here, this planet, because we just did analysis on this side, this giant puff planet. Right? This guy like weighs less, has smaller gravity field. You get, it's like, hey, I can really jump really high on this planet compared to Earth. I feel a lot lighter. Well, not, okay, I guess 75% of his weight. Okay. But the orbital speed of this planet is actually faster than that on Earth. It's an interesting combination there. Okay, let's do a setup. Let's do another conservation of energy setup. Okay. Suppose you have like a vertical looking loop. Okay. I'm going to take a block, some mass m. I got to smash it. Gets a spring with spring constant k. Like a flies around the loop. Call it V up there. Side change H. Maybe there's negligible friction. Is that okay? Negligible friction. Okay. Can you guys set about conservation of energy that could somehow solve this? Sum of energy at point A equals sum of energy at point B. Initial, final. So all the energy was in the spring. Should I say F equals kx, or energy is 1/2 kx squared? 1/2 kx squared. We're doing the energy approach. Right? And then that energy had to, let's say, maybe it's like 100 joules or something when you plug the numbers in, right? So you had to lift this thing against its own weight. So there's some mgh. And whatever was left over went into 1/2 mv squared. Right? So maybe it's like 100 joules supplied and 30 joules it took to lift it, and the other 70 joules was left to get around. Okay? Ooh, do you guys remember when I put some water in a cup and wheeled it around in a vertical circle? There was like a minimum speed to get around a vertical loop. You guys remember it being square root gr? If you have like some radial size of this thing. Okay, so remember that too. Okay. So put it all together. You could solve for like how much do I have to compress the spring X? That could be a good question, right? So guarantee it gets around, something like that. All right, guys, good so far. All right. I've just got a few minutes left, so I'm gonna maybe cheat a little bit. Let me show you guys my notes from last class. Let's do an impulse question. Impulse. So bat hits ball, bam. Okay. What if I give you some values like mass of a ball, the throwing velocity? Notice I call that negative because thrown one way, but bam, hitting it back the other way. Okay. Maybe here's an average force from the bat for some time interval. Now, if this was a graph, maybe you find the area under the graph. Okay. Force versus time. So impulse. Well, that's force times time interval, right? But that results in some mass times change of velocity, right? It's a transfer of momentum. Right? Well, if you know 3 of these, you can bam, bam, bam. You can solve for, I got, now that's a delta V, that's a change in velocity of the ball, right? 67 meters per second. Right? If you want to know what is the actual rebound speed of the ball, like how fast does it come flying off the bat, you have to do one more step, which is, well, final velocity is initial velocity plus the change of velocity, right? Or there's a little bit different approach, right? This is one way to do it, right? Here's my initial velocity, here's the change of velocity, therefore there's the final velocity. Boom, 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 just like that. You guys see that? Right? Oh, good. Right. So impulse, right? See force versus time graph, right? So like that. Okay. All right, and okay, so we've hit every unit except rotational dynamics. So here's a good rotational dynamics review question. Okay. What if you have this is a scaffold question, right? Set in the back of my room, I got a meter stick. Let's ignore the weight of the meter stick. Let's say it's pretty small compared to this big old 10 Newton weight that's hanging here at the 70 centimeter mark, right? And I want to know what is the tension in the left and right strings holding this up, right? So here's my conditions, equilibrium. The forces zero out, so these two forces up balances with the 10 newtons down. And the torque also zeroes out, 0 Newton meters. Now I'm going to pick this point as my pivot point. Say, relative to that point, the weight says, let's go clockwise, and this right tension says, no, let's go counterclockwise. And that has to zero out, so the torque zeroes out. Okay? So torque is R cross F, R cross F, R cross F, they balance, right? And plug the numbers in, getting, works out to be 7 newtons. It's kind of, okay? If this guy's 7 newtons, this guy must be the other 3 newtons to satisfy the sum of forces goes to 0. Right? Guys good there? Right. Who's got any question? Any question? Right, there you go. We did a little Whitman sampler. Got at least 1 or 2 questions from every unit. Right, all right, and there's the bell, just in time. All right, you guys have a great afternoon. I will see you guys tomorrow.